Hello. Welcome to the last one of these I ever have to do. It's kind of exciting for me. All right. I did multi-level modeling or MLM for my final assignment. So multi-level models are primarily used in research where data for individuals or participants is nested and organized at more than one level. So basically, individuals are nested within these aggregated units at a higher level. So, an example of this is a model of an employee within an organization. So, if we look at a model of an employee like performance, obviously this contains information about the individual employee, different measures from them, but also probably their team, the organization, and everything in which they are grouped. So basically, you can use this to look at what predictors within these relate to the outcomes and to what extent. So, what are most important in predicting outcomes? So, there's a number of different ways you can look at this, but I chose to look at um, a group of 10 different employees over the course of 10 weeks and their ratings on organizational climate and job satisfaction to see if from week to week these changed, the differences between the employees, if the organizational climate and job satisfaction related to specifically the employee, and this was related week to week, all of that. So, how all of those things were related. So, for this, there are two different packages you can use. I used NLME. Um, the other one doesn't show p values. I think it was called NLM4. Um, so I use this to get some p values because the F statistics are not shown in this form of modeling. So wanted to see some significance. So I've already installed the package. I'm just going to library, and then also we're going to do some plots. So ggplot2. Um, so uh, first we're going to do a lot of the basic stuff we did with screening data, checking for outliers, looking at multicollinearity, testing assumptions, looking at the standardized residuals, normality, linearity, homogeneity, homoscedasticity, all of that. So obviously I made this data set so I do not have missing data, but if your data is missing at the lowest level, so in this case it would be the employee level, um, you can kind of get around that. This works best with really, really large data sets. MLM does, um, but I don't have any missing data. But so we're just going to run just a summary to kind of see no NA shows up, no outliers, we're good. Or no missing data. This should be missing data. Um, but next we'll check for outliers. So Malinoba's distance, and then you can signify the data set, so MLM data, and then you want to do the column means, but we're going to omit columns 1 and 2 because this is just the employee ID and the week number. So we want to look at organizational climate and job satisfaction. So we're omitting column 1 and column 2, and then we're looking at the covariance. And then once again doing all that. So calculating Malinoba's distance, or setting that. And then we're going to set the cutoff for the outliers, so the chi-square, and then minus these, the categorical columns, so the employee ID and the week. And then degrees of freedom. Oops, sorry. And then just to see what the cutoff value is from setting that chi-square. So you can see 2 degrees of freedom, and then the cutoff value for the Malinoba's distance is going to be 13.82. And then we're just going to run this to see if any outliers do exist. And I have 100 data points, and there were none that had to be deleted as outliers. Yay. Okay. Next, we're going to assess multicollinearity. So looking at the correlations. Once again, we don't want to look at the columns 1 and 2. We want to look at job satisfaction, organizational climate, and we do want to look these are the two predictors, and we do want them to be somewhat related. That's going to kind of show later when we're looking at the predictors overall, but we don't want them to be like 100% correlated. That's something that's a little bit different than in some of the other tests that we use. So we see 0.37, not good, not horribly bad. So they're not unrelated, but they're not really related. Next, we're going to test some other assumptions. So to do this, we're going to create a random effects linear model. So we're just going to do a fake model, signify random effects. My data, once again, omitting those first two columns. And then we're going to use the fitted values to predict the mean responses from the data based on the predictors and the factor levels. And then same thing, standardized residuals. So look at, and then use this to look at the differences between the observed data of the dependent variable, which is job satisfaction, and the fitted values. Great. So using all this information, we can look at the standardized residuals using the histogram to assess normality. And we see a little skewness, but overall, this is a pretty good bell curve right here. We don't see these bars on the outside being too high. We see something in the center being the most common. So fairly uniform, slightly skewed. Next, we're going to look at linearity using a QQ plot. So we can see that there's a pretty good line here, kind of trickles off, but we don't see like a curve or anything. So linearity is pretty good too. Next is homogeneity and homoscedasticity. So we're running the fitted next to the residuals. And we see here that most of the points are between -2 and 2, so that part's fairly uniform. And on both axes, it's fairly even spread across, and we can kind of put in some lines to see kind of how these are split amongst the quadrants. Obviously, these three look a little bit more filled, a little more clustered together. There's kind of some guys hanging out here. This is a little more empty. So fairly even spread across, but not, could be better. Okay, getting into the MLM stuff. So first we're going to start out just creating different models. So this is how you test it. You're going to test a bunch of different models. So model 1 is going to be like our baseline. So this is our intercept only model. And this is assessing the average Y-score, so the score of the dependent variable, which is job satisfaction. And then this is assuming that all employees are equal. So it's kind of just keeping in mind that that it's not accounting for differences between employees. And then we're going to compare this after that against model 2, which will be a random intercept only model. So this allows the dependent variable to vary across participants. So you'll see it'll allow the employees to be variant depending on where they start out. So if model 2 is a better fit than model 1, that means you should run a multi-level model to figure out these relationships. So the intercept only model is using the generalized least squares fitted linear model, so GLS, which allows the errors to be correlated and have unequal variances. So you signify the DV, so job satisfaction, and then tilde of just the intercept. We're not going to signify any independent variable yet, even though we're going to use org climate later. And then that will test the Y average to see if it's different than 0, which we don't really care about in this instance. We kind of want to see, we're more interested in the relationship between the variables. And then the maximum likelihood method is going to be used because this is like an iterative process. And then this will show us the output values. So the main thing we want to look at is, we don't need this anymore, but that's okay. All right. the main thing we want to look at is our intercept value here. So over here was signifying this at 1 as our intercept. So our average job satisfaction score is 4.92. This is on a scale of 1 to 7. And then we can look at our standard error of 0.16. And then when we're comparing, we're going to look at the AIC and BIC and log likelihood values to signify best fit. So this will become important when we add in model 2. All right, so this kind of just gives us a basis to compare against. So next we move on to our random intercept only model. So this is a random intercept model that compares against model 1. This is now a linear mixed effects model. So this allows for nested random effects and within group errors to be corrected and have unequal variance. So once again, we're still setting the random intercept to 1 and letting it vary by participant number. So every employee can have a different average score across items. So this is signified over here. So random intercept 1, and then using the employee ID number. So once again, to signify that each employee can have that different average score across items. So they're going to be different as opposed to when before we were assuming that they were all kind of equal. And then same thing, we can look at the intercept value, which is the same, standard error a little bit different. And then we can look at the standard deviation. So basically the random effects is controlling for the fact that every person starts at a different place. So the intercept is going to vary around each employee. So that intercept value of 4.92 and then plus or minus 1.38, depending on the person. So next, we're going to compare the models to see if we have to control for participants. So to see if this is going to affect the model. So model 1 to model 2, so the two we just made. And this is where we look at the degrees of freedom, AIC, BIC, log likelihood, and then p-value over here. So the AIC and these values all show a better fit for model 2. So degrees of freedom is just subtracting the log likelihoods to test if they're different than 0. And then, so this means that we want to use MLM to control for participants as it is showing that it's significantly different than model 1. So comparing these two. And then where participants were assumed to be homogeneous in model 1. So this model 2, once again, is where participants differ. So we're going to control that in our next model. So our second level, we know we have to control for the participants, so we're going to check to see if we have to control for weeks as well. So maybe one week was different than the other and then just changed scores. Same format as before, but now we're adding in a list and then adding in week along with the employee or participant number. Okay, so once again, our intercept value is the same. Standard error, yes, same. And then but the standard deviation is slightly smaller. So there's less variance when controlling for weeks nested within employees. And then we can compare all of the models again. So where we had originally seen model 2 being significantly different, model 2.1 is not significantly different. So this means we can just control for every participant as opposed to every participant across every week. So these values got higher. Those are the same. And then this is not significant. So basically this would be more important in a situation where say you were giving out items on a test and certain participants saw certain items. So you were assessing difficulty. I mean, I don't want to drag it back to IRT, but difficulty of the items. So since every participant was exposed to every week, we can kind of think of that as being somewhat of a constant, and maybe that was something that affected all of the participants equally. So if something potentially isn't affecting the participants equally, then we would see a difference here, and it probably would be a better fit for the model. All right, so next is going to be our predictor model. So this adds the fixed effects to the model. So nesting by participants, do random intercepts are better than, since random intercepts were better than not, we're going to replace the 1 with the independent variable now. So org climate, and then that's what we're interested in looking in. So we're nesting by participant, use job satisfaction as the outcome, and then organizational climate as the predictor. Outcome, predictor, data the same, and keeping this the same from that model 2 that worked. Then same thing, running the summary. So this one we can look at a little bit more. So we want to look at the value and standard errors again, and we want these to decrease as we did control for employees, so less error. So intercept value here, standard error. And then basically the predictor in the model is what's moving the intercept. So as we're adding more predictor to the model, that's going to change it. And then so what this is kind of telling us is that the more organizational climate perception, you can also look at standard deviation, the more organizational climate perception, there's more job satisfaction. The p-value is less than 0.05, which means this relationship is significant. We can look at this over here. And then it also can show us the relationship with the intercept. So if we look at this over here, so we can see where that kind of connects with the slope. So that's going to be the next thing we look at, but in a random slopes model. So now we want to compare successive models. So this is going to compare model 1 to model 2, model 2 to model 3, and just to show that what model is the overall best fit. So we do see that model 3 is the best, the lowest values here, significant p-value when comparing those. So this is especially useful when we have more than one predictor that we're using. So I just used a simple form of this, but if I was adding in another predictor, we'd be able to see which one of these was more significant when we controlled for it. So useful for multiple predictors to see the differences between all of the models. As we add more predictors to the models, how does this change? Next, we're going to do the random slopes. So basically now we're changing from the random intercepts to random intercept and random slope to test how much the differences between participants varies. It's basically a moderation analysis without a real variable. And then this is implying that every participant has a slightly different relationship between the independent variable and the dependent variable, so job satisfaction and org climate. So we're changing the tilde 1 in the random section over here to our independent variable, and then so that way the slope is nested within the employee ID. So the slope org climate against employee ID, and then summary of this model. So this is just showing us, once again, we're looking at the same things, all the correlations, the intercepts, standard deviations, and the positive org climate. So as participant org support goes up, job satisfaction goes up. The org climate value is 0.4157 and varies by 0.306. So it's not a super wide range. So the slopes should be similar around the average score. Basically, people perceive organizational climate differently, but org climate does predict job satisfaction. So that relationship is related. And then once again, we're going to compare all of the models. So 1 to 2, 2 to 3, 3 to 4. And we see that model 4 is the best fit. So controlling for all of those things with the random slopes and the random intercepts gave us our best fit with the AIC, BIC, log likelihood, p-values, all of that being significant. So this basically just tells us that, oh, and I forgot to say that looking at this value up here, the org climate. So there's a high correlation between the slope and the intercept. So the relationship is varying together. So it shows that there's an interaction to where the participants start and their slopes. Basically, this tells us that something is happening between where participants originally start for their scores and then how this changes. So once again, we want to compare models. So 1 to 2, 2 to 3, 3 to 4. We see all of that. And we want to continue using model 4 as our best fit. So we're going to do the same thing that we did above with the standardization that fitted to look at some of the plots. So using model 4 with the residuals, same format as I used above. Should create the standard residuals and the fitteds. So this QQ plot looks actually better. Things are more in a uniform line. See a little kind of stair step thing, but I'll put the line in. Pretty close to the line all the way through. And then testing for normality once again. We see a couple dips, but slightly less skewness. This is only going -2 to 2 before it kind of was going out, I think, to 5 or 10. Then we can look at, oh, I put this down here. That was for linearity at the QQ norm. And then homogeneity and homoscedasticity again. So we kind of saw the relationship between the slopes and the residual scores, like which are causing the different clusters. It fits slightly better, but we still see this area over here and a lack over here. So basically, just to recap, you use this to make a bunch of different models of the nested data to see how certain predictors are more influential on the outcomes and to see if these things vary by participant and a variety of other different predictors. Okay, bye.